Hi, everyone, and welcome to today's webinar on motors and drives brought to you by Plant Services and Timken Power Systems. I'm Tom Wilk, the Chief Editor of Plant Services, and I thank you all for joining us today. This webinar is sponsored by Timken Power Systems. The Timken company designs a growing portfolio of engineered bearings and power transmission products to continuously improve the reliability and efficiency of global machinery and equipment. Now, before I introduce today's speaker, there are a few housekeeping issues I'd like to go over with you. If you're joining us for the live day event, you should see several primary sections on your screen. At the center is the section where today's presentation slides will be displayed. Below that section are the audio controls, and these allow you to adjust the volume of the presentation. Just hover over the speaker symbol until you see the volume control, and then adjust it to your preference. To the left of the slide window is the Ask a Question and Text Support box, and this is where you can type a question for the presenters at any time during today's webinar. We'll get to as many questions as we can during the Q&A session following the presentation. Also, if you have any technical problems, please type in your question or concern into this box, and one of our technical engineers will assist you directly. At the far right is the related content and handout section, and this section contains a link to the full set of today's speaker slides. So you can use that link and click to download it any time during today's presentation, whether live or on demand. Finally, at the bottom of your screen, you should see icons for additional features, including user help. By hovering over each icon, information about it will be displayed. For those who are joining on demand today, from left to right, you should see the slide window, the speaker window, and the set of feature icons. These icons include the Ask a Question feature, the orange icon at the top, and the Handouts icon, which is the blue icon with the paperclip. All questions received on demand will be forwarded to our guest speaker for today, who will follow up with you privately after the event via email. For those attending the live day event today, you can enlarge any section by clicking on the box in the top right corner of the section. You can also go to full screen by clicking the icon that has 4 small arrows in the shape of a square. If you accidentally close out any sections, you can get them back by refreshing your browser window. This webinar will be archived, and we encourage you to direct coworkers to the recorded presentation. At the end of today's presentation, we'll ask you to complete a very brief survey to provide some feedback that we can use to improve future webinars. And now I'd like to welcome Henk de Swart, who will speak on the topic of the truth about VFDs. The expert explains the real costs. Henk has served as the Chief Electrical Engineer at Timken Power Systems since 2019 and currently leads the engineering team at Timken's 3 electric motor repair workshops, where he conducts failure investigations and root cause analysis on high-profile cases. His extensive practical experience has allowed him to author 5 published IEEE papers, invent 5 registered U.S. patents, design many unique motors, and complete technical audits on more than 30 of the major service shops in the U.S. Henk was with us last year about this time, and I'm excited to work with him again. Welcome, Henk, and thanks for being here today.
Good afternoon. Thank you very much for everybody joining us today with a really interesting topic. I spent lots of late nights working on this, and it's based on a paper that I'm going to submit for publication to the IEEE, specifically about this topic later this year. It's called To VFD or Not to VFD? Are you saving or wasting money? This beautiful 15-page document gives you a detailed description of all the technical references, the research that I've done, as well as the formulas, the calculations, and everything. Now, obviously, today I can't cover the content of a full 15-page document, so I've given you the highlights of what I found. And the idea was, with the topic today, is there's a lot of talk in the market of we need to install VFDs everywhere so that we can save the planet from all these horrible electric motors that's draining our national resources. So I wanted to try today give you more of a balanced view, looking at the motor, the drive, the load, and different types of applications to enable the user to make an informed decision of when should he use a VFD and when it's not a good idea. And yes, there are definitely specific items that you can save significant energy, cost, and money by using a VFDs, but there's other cases where it's not. So I'm going to run through, I'm going to do the introduction, talk about a bit of a definition of what efficiency is. Then we're going to be looking at the system to define the different aspects, the variable frequency drive, the electric motor, the driven load, gearbox. And then I'm going to do 4 case studies. The first 2 is where the VFD can save you money in specific cases. And then the last 2 where the VFD won't save you money. And then wrap up with a conclusion. Jumping right into it, as I said, the punchline of many technical papers and sales presentations from VFD suppliers is installing VFDs in an industrial plant will save the customer in the long run, specifically due to energy savings. Should the industry thus do our part for the environment and our wallet and install VFDs on all motors? In other words, is the VFD-less motor, thus the Ford F-250 gas guzzler, environmental disaster equivalent of the Tesla? Like I said, hopefully this paper will present you with a more systematic analysis. If you look at the IEEE paper, the idea is to give the user, even if most of the plant information is unknown, like for an existing plant, to be able to calculate and do significant estimation to do an informed engineering decision. So, walking on to the definition of efficiency. Now, efficiency is defined as the ratio of the output power divided by the input power. Now, if we look specifically at an electric motor, we see that the input power is thus equal to the output mechanical power plus the losses. Now, this same principle applies to other parts of our system as well. In other words, we can then use our formula and recognizing that the energy converts energy from the electrical energy into the useful work. And the useful work is not wasted. The useful work is necessary because that's why the plant exists. To get the useful work to 0, you switch off the plant. Then you'll save 100% of the energy, but of course, you will have no production. So in order to calculate the system efficiency, we have to take the product, which is that nice looking capital letter pi, is the product of the efficiency of each of the individual components. And each of these individual components, again, is calculated by using the output divided by the output plus the sum of the component losses. So if we look at our system, now obviously the system can be very broad. I'm looking at an industrial plant. Obviously, there are specific situations that will have different requirements and different specialized machines for specific specialized application. And I'm not trying to address every possible opportunity, but I'm looking at a general industrial plant with General Motors, pumps, compressors, mills, fans, stuff like that. And for this analysis, I actually ignored the incoming supply. The incoming supply, you'll have switchgear, you'll have cabling, you'll have transformers, which also do have losses. But the focus of this presentation is not on that part. What we will look at is the VFD, the electric motor, which is always used, the gearbox, when applicable, and the driven load, again, which is always used. Now, for our analysis, we define the loading to be between 50 and 100%. I got a question from a customer a couple of months ago where he says, well, my plant is running at half load or less. What should I do? And I'm not trying to go to that extreme because then probably you have other problems in your plant if it's so far over design. So maybe next year I'll talk about that. But for now, we're looking at a reasonable plant loading between 50 and 100%. If we look at our variable frequency drives, they are fantastic at regulating the speed of AC motor, which has, for a significant portion of the market, replaced DC motors that was used in a vast majority of historical cases. These days, variable frequency drive with the AC motor can give you fantastic speed control. I'm going to focus specific on fixed flux control. Now, what this is I have constant torque with variable power. And the reason for this analysis doing it that way is that with the fixed flux control, I have a much better understanding And it's much easier to estimate what happens in the losses in the stator core because the flux density is fixed. If I go to all kinds of different control methods, then it becomes a lot more difficult to estimate. And one can see that other control methods might be able to give you better results, but let's start with the system that we can analyze. Now, for variable frequency drives, the efficiency is really high. These are good machines. The Department of Energy issued a report, and it's listed in the technical paper, that basically between 50 and 100% load, your efficiency is virtually constant. Now, for larger VFDs, we can see typically that the efficiency of VFDs is as high as 98%. And that's what I'm going to use today. I'm going to use a nice, significant size 1250 horsepower machine. So I want to use something with a really nice efficiency of 98%. But something that's often ignored by the VFD suppliers is that the VFD does induce additional losses in the motor because of the non-sinusoidal supply. Now, in the research, I found that there are, in this load range, there are calculations that can be used to quite easily determine what happens to the losses because specifically of the VFD. As I dug further into my research, what I found was that probably the reason why this is not addressed by VFD suppliers is because it's extremely difficult to apply this specific formula to my motor, because this efficiency multiplier does not apply to the entire losses, all of the losses, and it doesn't apply to the entire power consumption of the machine. I need to estimate each part of the loss component and then look at how can I apply this formula. And that's what we're going to do. So looking forward to my electric motor. Electric motors are fantastic at driving loads. These days we can use horses to ride on and not drive our mill. Now, motors, unfortunately, have been incorrectly labeled as wasting as much as 40% of global energy resources. One report even said 60%. This is a bit of a misnomer because the motor actually only wastes the losses, which is typically less than 5%. In fact, the motor converts 95% of the electrical energy into my productive work, and that's why I have my plant. Now, motor efficiency and performance data is very well known. It's very well published. For any motor you buy, you can get the performance data without any issue, except this data is for fixed frequency and fixed voltage. And we know for our analysis, we want to look at what happens when I use a VFD. Now, what happens with, as we said previously, we've got this adjustment factor for the losses. In the data that's published, the OEM does not publish what are the specific loss components. So I needed to devise a method to take this electric motor and maybe its existing plant, which I have maybe just the rating plate information, and I do not have all the different loss components. I need to calculate them so that I can apply this adjustment formula to get real examples and not ignore stuff because they're difficult to get. So looking at this, I had to take the electric motor and change and calculate the known losses. And these are very well defined by NEMA and IEC and IEEE of the different loss components. And there's been many papers written on what these losses are. However, what I found was, again, adjustment for a variable frequency and variable speed became very, very difficult to find. So what I had to do is look at the, as a start, the iron losses, which is because of the flux. Now thinking back, because I defined my control method as fixed flux, the flux would not change because of the change in speed, because it's fixed flux. However, the losses would change because of the non-sinusoidal waveform that's introduced into the motor. Now, I tried everywhere to try and find iron losses. What are they? We can calculate them. We can test them very easily during design or testing phase of a motor. But for a customer with an existing plant, it's virtually impossible to find this information. I actually had to dig deep, and I did a survey on another paper that I'm planning to publish on more than 600 different design motors, and I calculated for each motor the iron losses, the friction and windage, and all the other losses, and I could use this to devise an empirical formula that's listed there to the fourth power that can be used to calculate then the losses at full load, the iron losses at full load. The significant thing about that is that the customer can take an existing machine that they doesn't know much about, and they can use this formula and to a certain high degree of accuracy calculate what the iron losses are. Now, moving on to the conductor losses. Now, the stator and rotor conductor losses is because of the current flowing in the conductors, and they are proportional to the square of the current. Again, the non-sinusoidal waveform, because of the VFD, will create additional losses, which we know what they are, that formula. However, we sit with the same situation where we don't know for that existing machine what these losses are. The OEM don't specify what they are. And if I have the machine tested at a test bar, I can certainly calculate and would know what they are. But for an existing plant, I can't do this. And I used the same research that I did with the 600 machines. And I could devise a formula that could calculate and estimate these conductor losses combined for any machine size from 130 horsepower to 3,720 horsepower. And that's what we'll use to calculate the values. And I'll show you later on how these actually tie together. The next losses we want to look at is friction and windage, which is mostly because of the fan. Obviously, there is some losses in the bearings because of friction, but we find that it's a very low loss component. And from his historical manufacturing of machines, we know that it's typically between 0.5% and 1.5%, these friction and windage losses. We know that the friction and windage losses does not get influenced by the non-sinusoidal waveform of the VFD. And that's one of the reasons that if we do the analysis, we can't just apply that formula to all the losses, because we would be treating the VFD unfair and saying you're creating this additional losses in the friction and windage, which it doesn't. However, the friction and windage losses will change because of the change in speed. This also becomes a complicated thing to calculate, because the friction and windage inside the machine is a closed system for the most part. So the friction, the windage, the flow, the airflow, the pressure, all of them work together. And what I found was NASA actually published a research paper where they did an estimate for the friction and windage at a variable speed. Again, if we look at a limited range between 50 and 100%, then this formula holds true. Now, going to our last type of losses is the stray load losses. It's called affectionately the other losses. Lots of international publications even call it there, and it's the sort of the whatever's left over that we'll call stray load losses. And it used to be defined as a fixed percentage years back in IEEE and IEC. Or later years, they recognized that it's actually variable depending on the machine size, and they define it between 0.5% and 1.5%. Now, we will use for our analysis a 1%, which seems to be reasonable, and we'll use a linear scale for that down to the load. Now, in summary, we can look at this and say, okay, I've got my different loss components that I've defined. I can look at them and say which of these are load dependent. I can say which of them will be changed because of speed change, not because of the frequency or anything of that of the V, but just because the speed has changed. Then we can look at which of these losses will change because of the load. And then I will do that load dependency calculation. And for the last portion, I can now say which of these losses is actually part of my VFD efficiency multiplier. Again, I don't want to treat the VFD unfairly and just apply this multiplier to everything, because the friction and windage, it doesn't apply to that, the VFD efficiency multiplier. Now, using that in our examples, we'll now see where we get to this efficiency calculation. Now, for our load, I've selected a Sorry, let me get back to the motor. We've got actual real data from a OEM of a 1250 horsepower motor, a 4-pole motor. It's got a service factor of 1.15. It's built to NEMA MG1. We've got the efficiency. And what I did was I took this efficiency curve, which is as the orange curve, I plotted that, and then I used my formulas that I designed prior in this analysis, and I plotted the two together to say, how accurate am I in this lows range? And there was a significant amount of correlation. Again, the end user might not have this OEM data. He might just know the speed, the horsepower, maybe service factor and the current, and that's it. He doesn't know what the efficiency is at 100%, 80%, 50%. And the idea was to provide him a tool to use this to calculate it for existing plant, even if he does not have the data. So we can see there's a good correlation between the data. Let's move forward and we look at our driven load. I took that photograph of my garage last night just because it looks so beautiful. So the driven load converts the rotational energy into the designed output. Now this could be pumping a fluid, lifting a weight, grinding rocks, etc. So the output energy is necessary and required. Again, if we switch off the plant, then it's zero, but that does not help us. We need to make sure that we address the output that the plant requires. If I do something that reduces the plant output, it doesn't help me. I'm not saving energy. I might be saving energy, but because of my production losses, and production losses must be significantly higher than energy cost, otherwise I won't make any money. So we need to be very careful with that whatever we apply does not affect the output of the plant. Now, the driven load has got inherent losses that might be speed dependent, and I'm going to address that into the different cases. Now, we're going to do 3 scenarios, which I call fan pumps and compressor loads, 2 different scenarios for them, a flow per time and a restrictive flow. My 2 other scenarios would be a material processing load and low speed loads. And I'll define all of them as we go along. So let's look at our fans, pumps, and compressor loads. I grouped them together because they're very well known to have a quadratic law load, and we know we can use the affinity laws. So we can see from the affinity laws that for the 2 different speed points or operating point, the flow rate is linear to the speed of rotation and quadratic to the diameter of the impeller or the fan. In my analysis, I did not consider the case of I could take this existing fan and change the impeller size, which could be definitely be a solution, but that becomes a lot more complicated for a customer in a plant to do that. So I didn't consider that. So I made the change in diameter nothing because that's not what I'm looking at. I can also see that the discharge pressure or head is proportional to the square of the speed, and the power is proportional to the cube of the speed, which would already lead us into saying, well, if I can change the speed linear, I will have a quadratic change in my pressure, but I will have a cubic change in my power. So the power will drop significantly. And that's what I want to do, use these affinity laws on the fans, pump, compressors to be able to calculate what happens when I run the load at the reduced speed. Now, coming back to our 2 scenarios for this, we'll have two cases. One is where the load exceeds the plant requirement in a period of time. That's important, the period of time. In other words, the load run intermittently. Think, for instance, I need to fill a container with a fluid. I have a certain amount of outflow, and maybe I have some sort of flow sensor or height sensor, and will keep on pumping the tank full, but the capacity of the pump is significantly more than what is required, and the motor will switch on and switch off depending on the level. Now, that's my flow per time scenario. Now, the question would then be, can I change it with a VFD that runs, instead of on and off intermittent duty, running at full or running at a reduced speed, continuously maintaining the level of the plant? So that's one scenario I want to look at. The next scenario is very common, is a restrictive flow. That's where perhaps my pump is over-designed for my plant and it pumps too much. My plant cannot take or accept the capacity of the pump. So what is done then, you put a output valve, a mechanical valve on the output to restrict the flow, to reduce the flow. This could also be with a fan, where you will have vanes that you change in order to reduce the amount of flow that I get from my plant. Now, the question would then be, well, can I use a VFD without the mechanical vanes or valves, but just run it at a reduced speed? And that's exactly the scenario we will look at. For our case study, I got from OEM data on a pump. It's a nice, and I've obviously selected the same size pump, a 1250 horsepower pump. At that duty point, it has a specific maximum head and maximum flow and efficiency. Now, this is a very typical graph that we will see for pumps and compressors and things like that. And how it works is I have a flow rate, but the flow rate actually comes from the head. So the system has a head, and whatever the head is, I can match that, the head, to the curve, and at that point where that head is whatever it is in the plant, I will have a specific flow rate, and it will consume a specific amount of power. And this is exactly what I will use in my calculation. Okay, let's move to the next one. Now, for our case study, I'm talking about this, if I go back, this point, this has got a system curve. Now, the system curve is very important because it determines at that speed what the head is, what the flow rate will be. But for a variable speed, now that system curve changes across the speed range. Now, the problem is, in most cases, the customer does not know what the system curve is. We know that this curve is a parabolic curve, and we know that it will have a specific flow rate and a specific head at the duty point. The current duty point, the customer will know, we can easily measure, that's my flow rate, that's my pressure. Easy to find. What we ever know is also that at zero flow, that the curve is perpendicular to the zero axis. Now, this helps us in our formula that we know that the constant B, in other words, is zero. So we've got our head is A times the flow squared plus C. Now, in a static pressure analysis, if we say, okay, I have zero flow, in other words, the head is equal to the static pressure, which for the most part is, unless you have significant restrictions and you have too thin pipes, for instance. But for the most part, this static pressure is the physical height difference between the in and outlets. So again, we want to try and find something that a customer can practically use in his plant. So he can take a measurement from the inlet and outlet and calculate exactly what the static pressure is. Now, from this and the duty point, which I can easily measure, I can now get this formula and know what the system curve is. And that's what we'll use. So our next type of load, that was the first, was the pump, compressor, and fan. We will look at material processing, like this is a beautiful excavator. We're talking about mills, grinders, pulverizers. No, they don't adhere to the affinity law. So I cannot use that analysis to determine if a VFD will save me money. This load varies during the operation. There's no fixed duty cycle or periodic. And the input material to the system is typically supplied not at a constant rate, so the load varies as the process continues. So that's another load scenario we want to define and see, would a VFD save me money? And the last one we're going to look at is a low speed load. Low speed being, less than 1,000 RPM. Now, this is typical mills, kilns, crushers, loads. It could even include a large seawater pump, for instance, in a nuclear power station. Now, the purpose of this scenario is to look at something slightly different. Can I achieve the low speed by using a VFD instead of the traditional, either using a direct drive and a slow, massive machine, or using a gearbox? And this is what we're going to look at. Will that save me space? Will that save me money? Will that save me energy? So let's start with, before we get there, our last part of the system is our gearbox. The gearbox is known as a torque converter, and it converts speed and torque from the one to the other. It adheres to the conservation of energy, so we know that the input power is equal to the output power, plus some minor losses, and the speed times the torque is equal to each other input and output. This gives us a gearbox ratio. Now, the gearbox ratio is fantastic because it's independent of the load. It's independent of the losses. It's not like an induction motor where if the machine runs at a higher load, the speed decreases. The gearbox does not do that. It's a physical ratio depending on the gears in the gearbox itself. So for a case study, we got information from Philadelphia Gear, a significant OEM, of a specific gearbox. I again selected the same size gearbox. It's got a service factor of 2.5. In other words, 250%, which I was quite surprised about because electric motors, we used to a service factor of 1.15. In any case, beautiful machine. It's got a ratio of 5. In other words, you will decrease the speed 5 times. It's built to AGMA. And the full load losses is only 17 horsepower, which we should not be surprised about because the gearbox doesn't have a flux. It doesn't have a core. It's only gears. So the majority of this would be friction, not really windage because we don't have a fan running inside. So we can use this, number one, to calculate the full load efficiency of a beautiful 98.7, and we can use an efficiency curve that we can then draw using that. Okay, so let's start with our first case study. And like I said, this is a summary of the information. The real detailed calculations is in the paper, and to try and get this all today in one 45-minute presentation would be impossible. But let me give you the highlights. On that case study number 1 is the flow per time. So the load volume exceeds the plant requirement in a period of time. Currently, the load is run intermittently by switching the motor on and off. And I want to see if I can save energy by, instead of doing that, using a VFD and running the motor at a lower speed constantly. Now, again, I'm going to use my case study, the 1250 horsepower motor, a pump, and a VFD. Now, if I start with my first line, I can see I've got a specific volume that's required. I've got an X amount of time that I need to do this in. My speed of my pump is, this is where I set the baseline of the motor without the VFD. And from my duty point, I can see I need 932 kilowatt, which is 1250 horsepower. The motor is running at full load. I can calculate my full load losses as 4.6%. There's no losses because of a VFD, because I don't have a VFD in the system. This is my baseline. This is where I stop. The motor runs. I switch it on. I switch it off. So now I use my pumping time, and I multiply it by my input power, and I can get my energy consumption in kilowatt hour. So to do this work in a day will cost me 18,558 kilowatt hours. Fine. That's what I do every day. Now I look at this situation where I can use a VFD to run the motor at reduced speed. And I've actually calculated not just one point. I could go just to the last one and get the answer. I calculate different scenarios. So if I start at this scenario, I run it almost 100 RPM slower. I get obviously less flow rate. Using the affinity laws, I can see that now I only consume, this is the pump power, is 800 kilowatt. That's all I consume versus 932. And the pump runs, it doesn't run continuously, but it runs less time because my flow rate is less. Now, the output power of the motor would match the pump by definition. It's running at 85% load. I can use my all my calculations to calculate at this loading, what are the values for the losses. And then I can do the adjustment for the VFD running at 95% using the 2% losses of the VFD. So my total system losses, has gone up as a percentage. It's gone up to 6.73%. I should not be surprised. The VFD has got 2% losses. But did it make sense? Now my input power is 848. And if I do the time calculation and multiplied my time with my energy consumption, I will see that I have a significant real life cost saving. This is energy that I have not consumed, but I have achieved the same result. I've pumped the same amount of fluid. Now, I can run through that iteration, and I did it all the way down to where we want it to be, our 50% loading. I can see the pump only needs to run. Sorry, that was the typo. Now, the pump runs full time. In other words, I don't switch it on and off. Now, the pump at 1420 RPM only consumes 465. Now, that's the calculation we normally see in our brochure for the VFD, but I wanted to get a real life result, and that's why I had to adjust the motor losses because of the loading. I had to adjust the losses because of the VFD running at 79%, and I have to put in the VFD losses in there because I want real life results. I don't want the fairy tale. So my losses has increased from 4.6% where I started to 7.59%. The input power has dropped from 975 to 501. And we can see we have done now received a significant, like real life significant cost saving of 35% in my energy cost. While keeping in mind, I have additional losses because of my VFD. I've not ignored them. I've used them to get a real life result and say I can save 35% energy while still pumping the required amount. Now, one could almost say, well, I should use the VFD always. Not really. What I did was when I plot this curve, and the curve is for all kinds of different of running speed, what I found was above about 99% frequency, what happens is the losses in the VFD actually exceed what the motor would be without the VFD. So running the VFD at full speed on the motor is not saving energy because the output voltage is still non-sinusoidal from the drive. There's still losses in the drive. So the frequency must be below 99%, otherwise the VFD will cause more losses. So we need to remember that that point right at the top. However, if we're running below 99% of the speed, then we can see that the VFD will cause significant improvement and save significant amount of energy in the flow per time scenario. Replacing an intermittent duty motor with a reduced speed running motor. Moving on to our second portion, was case study 2 was restrictive flow. The typical scenario, like this picture, where you have a valve to reduce the output of the plant because it's overcapacity. In other words, it's too much water at a pump or it blows too much air and my plant cannot absorb it. And the question would then be, well, currently I use a vane or a valve to restrict the flow. What if I replace this with a VFD running my motor at a reduced speed? Now this becomes a lot more complicated because now I need to use my system curve to see where we're going to end up. So let's start off with what does the valve do? I start with my normal duty point if there was no valve. What the valve does, it increases, let me put a line, it increases the head. In other words, it increases the pressure, and now I get reduced flow, but also reduced power. So quite interesting that just with the valve, it actually does work. Now, if I go to my table, what I've used was my point B is my duty, the duty point where if I run it without the valve. Now I put in the valve because that's too much pumping. I need less flow rate. And I see that I've actually saved 18% of energy by using a valve. So the flow restriction, the valve, the vane, it is effective. It does what it needs to do. It reduces the output of the plant because it's too much. And it is energy efficient. I have saved 18% less energy, consumed less energy because of the use of the valve. And valves are used all over all plants. It's very, very common. It's high usage. Now the question would be, well, what happens if I do a VFD? Will that give me a better advantage? Now this is where it becomes quite hairy, and I'll try and run through this quickly. is we need to use the system curve to calculate and see what happens when I reduce the flow rate without the valve. So I'll take you to the graph, and what happens is I start off at my duty point. Now I'm not doing a valve. I want to reduce the flow according to the system. Now I calculated my system curve. I know I want a flow rate of that specific, my 940. So I get to that point. I know now what would be the head at that point. I know what the flow rate is, and I know what the head is. And now, by systematically drawing for different frequencies, different speed, I can use affinity laws to calculate what happens to my pump. As it pumps less water, it reduces the volume, the head drops, and the power drops. So what I found by doing multiple calculations, I find that 1455 RPM, I achieved what I wanted to achieve. With this system curve, I achieved 940 gallons per minute at a head of 2,396, and I consume significantly less energy. But wait, we need to remember that there are these additional losses in a VFD. And again, I'm not trying to tell fairy tales. I want to get real life results. So what I did was duty point B was the unrestricted flow, which is too much. I can't use that. That consumed 23,000 kilowatt hour. Point D is where I used the valve. It achieved what I wanted to achieve, was 940 gallons per minute, and it consumes 19,219 kilowatt hours. Now, using my previous curve and calculating at 1,455 RPM, achieving the same flow rate. In other words, I perform the task that the plant is designed for, but I run the motor at half load, and even when I add in the losses because of running the motor at reduced speed, my losses of the system increase, but I can see I have reduced the energy consumption of the plant by a phenomenal 48%. A huge advantage in using the VFD instead of a valve or a vane. Now, putting it together, again, we'll have a similar graph right at the edge, the top end of the curve. We're obviously not considering an idea where I have a valve just barely closed. Obviously, that's not the case. If you have a valve or vane in there would be a significant restriction. So keeping that in mind, the replacement of a flow restrictive valve or vane with a VFD can save significant energy. And hopefully the methodology that I put together in this paper, the customer can use to even calculate in his plant what the result would be. Before we run out of time, moving forward to the material processing load. Here our load varies significantly during the operation of the plant. The input material may not be supplied at a constant rate. We know that the load can change as the process. For instance, as an example, if you look at a mill, the load depends on the quantity of material, the quantity of rock inside the mill, the quantity of water in the mixture, but then also as you mill the rock smaller, the load changes. Now, this is where it becomes important, where I said right in the beginning, reducing the speed of the load with the VFD reduce the plant output. And that's exactly what we don't want, because the plant output must be significantly more profitable than energy costs to run the plant. Otherwise, I don't make money. So in this instance, material processing, a mill, stuff like that, changing the speed with a VFD is not economical because I reduce the output of the plant. And obviously, the plant owner can do that calculation, how much I get the output. But the answer will be it doesn't work because the value of the plant output is significantly more than the energy cost. That's why for a material processing load, I don't even need to do a calculation. The use of a VFD is not beneficial, as in it does not save me energy that would be anything close to more than the output than I lose. Moving to our last case study, which was number 4, was the low-speed loads. Now, with low-speed loads, I can take in the scenario and say, well, what if I have a kiln or mill or crusher? You'll see a little bit overlap with case 33, but let's go with it for now. What if I take this a high-speed motor that I run at a low frequency to replace a traditional direct drive low-speed motor? Because if you look at a 1250 horsepower, 360 RPM motor, that is a beast. That's a big boy. You know, it does what the plants need to do. It does the production, but it is a massive machine. It's a really big machine. And this scenario is probably more related to a new plant installation where this would make sense. But let's look at our second option is to take a high-speed motor, like an off-the-shelf 1250 horsepower 4-pole machine, use the gearbox to get to my low speed. And then our third option that we want to explore is, what if I use a VFD to run this machine, to achieve this 1250 horsepower? Unfortunately, we know that because of the VFD, the power of the motor decreases linearly with the frequency. Excuse me. So, in reality, I would need to buy a 6,250 horsepower motor, a 4-pole motor at 60 hertz, in order to achieve my 1250 horsepower. But let's get into that. We will look at the rectangular cubic envelope size of the equipment. So starting off with our first scenario, a direct drive, there you can see a beautiful example of a 28 megawatt Siemens gearless mill drive. In other words, you have no gearbox. This one is slightly different because the motor is actually, it's a wraparound. It's around the mill. That's not that common, but you have a low-speed motor, massive machine. There's no gearbox. There's no VFD. It's a non-standard motor. You're not going to get off eBay a 20-pole motor beast in a hurry. It's definitely not off the shelf. It's a special design and a special build for all OEMs. So you will likely not have spare machines available or on the surplus market or someone you can borrow from a plant next door in case of emergency. So this becomes a significant risk to the plant because an in-service failure result in extended downtime because it's of the special machine. Moving on to number 2 was where we use a high-speed motor, 1250 horsepower 4-pole machine coupled through our gearbox. Now here you see advantage, not exactly the same machine, but a typical application of a mill. And you can already see the size of the mill, the size if you had a wraparound motor versus the size of the electric motor through the gearbox. Now, interesting, this exact gearbox envelope is so versatile that it can achieve that output at almost any ratio from 5:1 to 1:1 to 1:5 with the service factor of 250%, which is quite incredible. Now, in this scenario, we don't have a VFD. The motor is coupled through the gearbox to the load. Now, this 4-pole motor, excuse me, is probably like an off-the-shelf machine. 1250 horsepower 4-pole should be easy to find spares. If something happens, the machine fails, it should be readily available, or I can borrow something from my neighbor. Looking at our last portion of this case study is if I use a high-speed motor with a VFD, the idea is because the output reduces linear the power of the machine, I can't buy a 1250 horsepower 12 hertz machine. Well, that's what I will buy, but it will not be the same size as the 1250 horsepower 60 hertz machine. Effectively, it will be the size of a 6,250 horsepower machine. We don't have a gearbox, but now we're sitting with the same scenario as what we had with our start with a direct drive motor. It's a non-standard motor. It's probably required special cooling because of the low rotational speed. It's definitely not off the shelf. It's a special build. Again, spares are not available and neither on the surplus market. There's no duplicate motors I can borrow from somebody else. And an in-service failure can result in extensive downtime and significant cost. Now comes for the big one. If I compare the physical envelope size of these machines, and this picture shows it much easier. My case study one is we have my direct drive motor. There's no gearbox. There's no VFD. I get a slow speed motor, which is a beast. It's a big machine. If I use my case study 4B, I use the motor and gearbox. Wow, look at that space reduction. And that's because of torque multiplication that we get from the gearbox. And then the last scenario, the motor because it's such a higher power rating motor and with the size of the VFD, which is often ignored, I get a huge envelope. So comparing the three, 4A is the direct drive motor is 3 times larger than a motor plus the gearbox, and the VFD plus the slow speed motor is 6 times larger. Now, both of these are special order machines. If something goes wrong, it's a problem. You're going to have long downtime. So what do we find also, because this is a material processing load, we know that the VFD is not going to save us money by running it at a variable frequency. We're only trying to achieve a fixed frequency. So what we find very, very clearly is very easy that the case study 4B, which is the motor plus the gearbox, provide a significant cost benefit in one big thing is the plant size, availability of spares. Plant real estate can cost a fortune, especially if you look at specialized plants like an oil platform. Maybe if you're in a farmer's field, it doesn't matter. But in any modern industrial plant, size, space, cost money. Now, wrapping this all up quickly, in conclusion, utilizing VFDs to drive motors and driven equipment at reduced speed, resulting in reduced production output, can result in significant energy cost saving if applied correctly for these load types that we found: fans, pumps, compressors, for a flow per time or restrictive flow scenario. If the speed of the motor and the load system reduces the output for the plant, for instance, in a material processing load, the use of the VFD is uneconomical because of the production losses. And then lastly, for a low speed load, taking advantage of the torque multiplication advantage of a gearbox can provide significant cost savings in capital procurement costs, standardization, plant design, and sizing of a low speed application. And that was it. There's some additional resources that will be available in the slide deck. Thank you very much.
All right. Thank you, Hank, for that presentation. We've got a lot of engineers who are plant services readers and attendees, and this presentation is just incredible knowledge for this audience. Thank you so much. We have time for 2, maybe 3 questions, Hank. Yeah. I'll remind everyone who's attending today, both live and on demand, that you can ask questions right now in the Ask a Question box. We'll get to as many of these as we can before we close out here at the top of the hour. So, Hank, we'll get right to it. The first one is about performance data of old motors, Hank. And here's the question. As a plant owner, it's not always possible to find the original performance data of an old motor. So how will I be able to perform an energy analysis without the support of the motor OEM?
Wow, thank you. That's a fantastic question. And that's exactly what I try to do with my analysis. And if you look at the paper, and if you go back in the slides, there are these specific calculations that I can estimate the performance, the specific losses, the friction and windage losses, the stray load losses, the iron losses, and the conductor losses. I can actually use those formula to a fair degree of accuracy. I can actually estimate it for any machine size within that envelope. And it's based on the empirical study that I did. So I can use that to estimate it even in an old plant.
Okay. We have a compressor question too. And the question is, what savings and benefits are realized when a VFD is used on a reciprocating compressor rather than a centrifugal compressor?
Oh, wow. What a fantastic question. Yeah, reciprocating compressors is a beast. They're definitely not standard loads. The problem with reciprocating compressors is that they don't follow the affinity laws. So I can't use my calculation to say, if I, reduce the speed, I can see that the affinity laws shows that I will save that my energy. That doesn't work. I can't do that. I need to now look at the output of the plant. And almost the easiest thing is look at the plant output performance. Right now, do I have a valve or vane control that reduces the output? And this is a first level analysis. Most probably in my reciprocating compressor, the answer is no. But if the answer is yes, it means there's definitely my plant oversupplies capacity. So there could be a point to or argument to be made to reduce the speed of reciprocating compressor to get output. However, with reciprocating compressors, often the pressure that's developed is very specific to the plant in that it's required for what's needed in the plant. So reciprocating compressors could be possible, but it's much more difficult because the pressure often is needed for the plant to operate correctly. So that would be a much more detailed study than the one that I've done. Thank you.
We've got a lot of compressor technologists also who read plant services, so that question is going to really fit in for both of their audiences. We have time for one more, I think, Hank. It's about energy again. It says, you didn't show an energy study for case study 4, which was the load speed loads. Would using a VFD in that case not save energy?
What a great question. Can I go back to that? Okay, two things, and the audience can probably see these answers. If you look at my case study 4A, which was the direct drive, I run the motor only, and in other words, I don't have losses because of a VFD or anything like that. In my case study 2, I will have a motor that is a higher speed motor, probably very similar efficiency rates than a motor, and I will have the tiny, and we've seen the losses of the gearbox is very, very small, but I save a tremendous amount of real estate, of space. And with my VFD, I know because it is a material processing load, there's no benefit in running at a slower speed, slower than full speed, being the 12 hertz, 360 hertz. There's no benefit in running it slower because my production losses would be too much. And if I remember back at my case study 1, probably, if I'm sitting at that almost full speed, then it doesn't work to use the VFD because the additional losses of the VFD increases. So it's not really needed to do a case study, but yes, it will not work to save energy in that case. Thank you. Right. Great question.
Well, and we've got about 2.5 minutes, and that's enough time for us to close out. So, Hank, once again, thank you for being here. I really enjoyed today's presentation.
Thank you very much for having me. I learned a lot by doing this case, and I would urge to read this. Once the publication in IEEE go out, it's a tough read. But you'll learn a lot about the details of these numbers. We just throw them on the screen. But if you go through that case study in detail, you would really learn of how you can actually do this in your plant. Thank you very much.
Well, no, thank you again. And thanks to our sponsor, Timken Power Systems, and everyone who joined us today. A couple of notes on the on-demand version. This webinar has been recorded and will be available shortly for on-demand viewing. You're also encouraged to visit plantservices.com to gain access to even more tools and resources aimed at helping you achieve motors and drive success. Also, in the handouts area, I'll refer you to Hank's speaker slides. If you want the full set of slides from today's presentation, go ahead in that handout section. We'll be live for about maybe 90 more seconds, but these will also remain available in the on-demand link. And download a copy of the slides for your own reference. Last thing, did you like the presentation? Please let us know your thoughts by answering the brief survey that will appear in your screen shortly. And Hank, I sure did, so I can't wait to take the survey. Everyone's candid answers are not only appreciated, but they help us craft future and better events. So once again, thanks to all for attending and presenting, and have a great rest of the day.
Thank you.